Welcome to Introduction to Photonics. So we've been talking about interference of light. We've been treating light propagation in terms of waves, and we've been talking about recently we've been talking about the statistical property of light, which provides this concept of temporal coherence and spatial coherence. And what we're going to do in today's session is try to see if we can use the knowledge that we have gained so far, see if we can use that to actually design certain optical components. Okay, and one of those we started doing in the last session was, we said we'll consider interference in thin films, right? And while we were considering interference in thin films, we noticed that whenever light goes from one medium to another medium, it's going to undergo certain reflection, and we recognize that if you look at going from a rarer medium into a denser medium, that is N2 is greater than N1, then you have a pi phase shift at that interface. Now, based on this, we were asking the question whether it is possible to have things like anti-reflection coating. So I mentioned that if you're going from air to glass, let's say you have this air medium and going into a glass medium, we expect to have a certain reflection at that interface. And so if you are going in from here, you are going to have a reflection at that interface, and that reflection is going to give you a pi phase shift. Is there any possibility that you can cancel this reflection using the kind of properties that we have talked about? Okay, is the question. And the answer turns out to be yes, we can do that, provided you have destructive interference between the incident wave and the reflected components. Okay, so what are the reflected components we are talking about? Now this incident wave, suppose if it's incident before it hits the glass medium, before it hits that glass interface, it encounters another medium, let's say a coating on that glass surface. Okay, and of course what we are saying, if there is a coating, then compared to air, that coating is going to have higher refractive index. So from here, this interface also we have a pi phase shift. Okay, so if you want to cancel this wave component with a wave component that is coming from here and through this, okay, the question is, what should be the phase that it needs to accumulate so that this cancellation happens? So we are talking about one wave component which has got a pi phase shift, and another wave component which has gone through this coating, hit that glass interface and it's come back. What should be the phase accumulated so that these two cancel each other? What should be that phase? So if it encounters a pi by 2 phase shift this way and a pi by 2 phase shift this way, the total accumulated phase would have been 2 pi, right? And the relative phase shift between these two would have been pi, in which case this initial reflected component will be cancelled by this other component, right? So if we have a structure, if we have a coating that's incorporated such that the thickness of the coating, first of all, the coating is having a refractive index that is lesser than that of glass, okay, and the thickness of the coating is such that it has a pi by 2 phase shift, okay. Then we see that these two reflected components will cancel each other, essentially saying that there won't be any reflection for a particular wavelength. Why a particular wavelength? Because if we consider this condition here within this region, let us call this certain thickness DC, okay. DC is such that the phase that you accumulate in the single pass, that is going to be given by 2 pi over lambda multiplied by, let us say, NC is the refractive index of that coating, NC multiplied by DC will have to be equal to what? Pi by 2, okay. And we can go ahead and cancel this pi with this pi over here. So, this implies that DC will have to be lambda over 4 times NC, right. So, if we have this condition, then if we have a thickness of a coating that comes into the picture such that you have a pi by 2 phase shift incorporated in one direction, there is a pi by 2 phase shift in the other direction as well, and then there is actually a pi phase shift happening because of reflection between the coating interface and the glass interface, then overall there is a 2 pi phase shift for this component that is coming through, okay. Then you can have destructive interference between these two components. And that destructive interference means that any glare that you get normally with a glass surface, you would have ended up cancelling that glare with this extra coating that we have provided. Does that make sense? Yeah. Of course, there is this thing about what should be the refractive index of the medium, and it can be shown that this refractive index, just there is a parallel in terms of what you do with transmission lines or in electromagnetic theory would have to be equal to the geometric mean of n air multiplied by n glass, and n air is of course 1. So, you would say that this would have to be equal to n glass. So, if I take a material which is roughly corresponding, which is having a refractive index corresponding to root of n glass, and which has a very specific thickness, okay. So, if you incorporate that, then you should be able to cancel that for a particular wavelength, cancel the glare for a particular wavelength. So, it so happens that for the visible radiation for which we want to cancel this glare, we would have to choose one particular wavelength, okay. So, that wavelength, let us say if it is green wavelength, let us say lambda corresponds to 550 nanometers, and then NC is root of n glass let us say you are starting with 1.45 or something like that, then you can figure out what should be the corresponding thickness, okay. And that thickness would be roughly in the order of 100 nanometers. Okay. So, if you are able to apply that coating on your glass, then you can make it anti-reflection coating. So, the question is, we are saying that there is no reflection of light, that there is destructive interference over here. So, correspondingly, can we assume that all that light is going this way? That is exactly what we are saying, right? It's cancelling all the reflection components, so all the light is going straight through. So, the question is whether energy is remaining constant or getting lost over here. In this case, the energy is conserved as we are moving in. As long as there is no loss in the propagation itself, we are saying the energy is conserved over here. So, that is, let us say, the A part. Actually, this is one of the questions that is given as part of your tutorials, tutorial number 2. So, let us say this is A part. Can we use this principle now to make a mirror, a high reflectivity mirror? Okay. So, that is the second part. Question is, how can we extend this principle to design a high reflectivity, let us say greater than 99% mirror? Okay. So, if that is what we want to do, how do we go about doing that? Okay. So, in this case, I think I gave a hint about this towards the last lecture, to end of last lecture. So, suppose you have let us say material with refractive index NH, followed by another material with refractive index NL, and then followed by another material with NH, and so on, right. Let us see what happens in this case. Let us see how we can essentially get a mirror. So, for getting a mirror, like all of you recognized in the last lecture, we said we will have to have constructive interference of all the reflected components. So, all the reflected components add up, right. So, let us say you have this incident wave over here, and of course, it's encountering a high index medium, so denser medium. So, it's going to have pi phase shift. Okay. Then whatever is reflected from the next interface, if that is pi or 3 pi or whatever phase shift is accumulated, then it would be constructively interfering, right. So, what is the phase shift that we get here going from a denser medium to rarer medium? 0, right. So, there is no phase shift over here. So, in that case, if you wanted to get out with a pi phase shift, what do you have to do? Make the thickness such that the phase accumulated here is pi by 2, and after reflection, obviously it is going through the same thickness. So, that is also pi by 2. Okay. So, then the component that is reflected from the next interface, that is in phase with the initial reflected component. So, both of them are adding together. Okay. Now, can we see if we can extend this to the next layer? So, let us say the next layer at the next interface, how much is the phase shift that you get upon reflection? Pi, right. Now, once again, if you do pi by 2 here and pi by 2 over here, now let us count all these phases. So, this is pi by 2 this is next is pi by 2, so there is pi, and then there is a pi phase shift upon reflection, and then coming back this pi by 2, pi by 2. So, the total that we get out of all of this is 3 pi, and whether that is in phase with the other reflected components, yes, it is just got a 2 pi phase shift between. So, that is going to do a constructive interference. And similarly, you can go on to build over multiple layers. So, after this there will be NL, and then you go on to NH, NL and so on, right. Then all of these things, if as long as you have with each layer you are picking up only a pi by 2 phase shift, you are going to end up with constructive interference from all these layers, all these interfaces. Okay. So correspondingly, what is DH and DL? Just based on what we saw in the previous case, we can say DH is going to be lambda by 4 NH, and DL is going to be lambda by 4 NL. Okay. And if we say lambda, in this case we want to reflect green light, okay. Let us say green light, if lambda equals to 532 nanometer, then you can calculate what the corresponding thickness is. Now, what we do not know is NH and NL, okay. What we are not considering here, the other important consideration is, if we want all of this to add up, okay, you want good reflection from each of those interfaces, right. So, how will you pick NH and NL so that you have the minimum number of layers in your mirror? What should be the relative values of NH and NL so that you have minimum number of layers? The relative quantities should be, what did we say? The reflection coefficient depends on the index contrast. So, the relative components should be large with respect to each other, right. So, you want to have, so from each reflection you are getting the reflection coefficient is NH minus NL divided by NH plus NL, right. So, if NH is far greater than NL, then you have a larger reflection coefficient. So, you would have, you need lesser number of layers, right. So, what we have in the industry is that NH, there is a material called zinc sulfide which has a refractive index of 2.32, and for NL we use the industry standard is a magnesium fluoride which has a refractive index of 1.38. Okay. So, if we use these two material, then so the corresponding DH, if you calculate, that corresponds, that will be 532 over 4 times 1.3, sorry 2.32, that will be roughly about 100 nanometer is what I reckon. I do not have a calculator in front of me, you can do that calculation. And DL would be slightly larger than that because NL is lower than NH. So dl in this case will be roughly in the order of 80 nanometers. So you can do the exact calculation to figure those numbers out. Okay, but what we have done here is we have done a relatively advanced design of an optical component by tracking the phase, okay, by tracking the phase and using this principle of constructive interference. We have just managed to construct a mirror like this. Now, this seems to suggest that I look at, okay, this thing as R1, and then I look at R2, R3 and so on. I can just add all of these reflection coefficients, okay, and from that I can find out the overall reflectivity. Does that make sense? In this case, can I just add all the reflectivities from the individual layers and based on that I can find out what the total reflectivity is? No. Why not? Because every reflection you are losing some intensity in the backward direction and it is constructively interfering. That means that energy is lost. Okay. So, every reflection you have a certain loss of energy. That means that for the subsequent reflection the effective reflection coefficient is lesser. So, you have lesser and lesser contributions from the farther points of farther interfaces of reflection, right. So, it's such that you get a certain reflection from the first few layers, and to get more and more reflection it's going to take more and more layers, right. I mean, to improve the reflectivity beyond the first few layers it's going to take more and more layers. Okay. So, it's such that and I don't have the time to derive this, but if you take all those into consideration, you can come up with this expression that this is going to be given by NH over NL to the power of 2n divided by 1 plus NH over NL to the power of 2n, where n corresponds to the number of pairs of high and low index regions. Okay. So you can basically calculate the reflectivity that you can get, and what you will find is reflectivity of greater than 99% is possible if you go out for n in the order of 10 or 15 or something like that for the given pair of NH and NL values. Okay. But on the other hand, the when we were looking at the Michelson interferometer, you had a 50-50 beam splitter. 50% went one way, 50% got transmitted, 50% got reflected. So, what does that mean? You have lesser number of these layers so that you can achieve that 50%. So, you plug in 50, R equal to 50, NH and NL we know, so we plug that in, and then if you find value of n has to be an integer obviously, right. So, you put that value, then you can find out how many layers do you need to get that 50%. that's how that particular component was made. Okay. So, and of course, one of the key things to note here is everything is dependent on this value lambda. What does that mean? You are designing this mirror for one particular value of lambda. Okay. So, if you for all the other values of lambda, it is not actually meeting this constructive interference criteria. Okay. So you may not be able to actually add up as much. So, the reflectivity will be a function of lambda. So, the overall reflectivity, if you look at that as a function of lambda, you will find that it will be like this, and then there will be side bands also, but that will be all for one particular value for which it's designed. Okay, so that reflectivity will be dependent on wavelength. Okay, so let's extend this even further. Can I do some trick over here with this structure, with this principle, such that instead of getting a reflection like this, I get a transmission over a narrow wavelength range around a particular lambda naught. Okay. Is it possible to have something like this? So, what type of filter would you call this? Band pass filter, right? So, can I extend this concept and find a way to get a band pass filter? Okay. So, this is basically a mirror, which is basically a band stop filter. It reflects a particular band, but transmits everything else. But if I want to change this to a band pass filter, if that's possible. So, turns out it's possible if we go back and look at one of these configurations that we were discussing earlier. For example, so maybe I should turn this question around to you and say, which one of these interferometer configurations can I use to achieve a band pass filter condition? Do you see something here which we can use as for making a band pass filter? Fabry-Perot, very good. So, Fabry-Perot filter, Fabry-Perot echelon can be made as a band pass filter. Why? Because we are saying that light actually enters this Fabry-Perot structure and goes through multiple bounces, and we are looking at the relative phase between all these bounces and on one of the mirrors. If they are all constructively interfering, then that particular wavelength at which constructive interference is happening is going to escape that cavity, right. So, a Fabry-Perot structure, if you are able to make with two mirrors, you can possibly get a band pass filter. So, let's see how we can do that over here in this case. So, you know how to make a mirror. Can we make two mirrors out of this structure parallel to each other? So, what do you have to do to get something like that? So, if we were to extend this to NH, NL and so on. Now, let us say at one particular layer, instead of going to NH, I just have NL. So, to give you a perspective of how to make these structures, what you do is you start with a substrate, with a glass substrate, okay, and you evaporate this material, you put magnesium fluoride on that, you monitor the thickness for whatever we said 80 nanometers, and then you stop that evaporation and then you start evaporating zinc sulfide and let it build upon layer by atomic layer, you can do that and you can get this 100 nanometer thickness and then go back to magnesium fluoride and so on. So, you can stack everything up layer by layer, right. And in that process, you can choose to say after a certain stack is built, after let us say 10 pairs are built, I can choose to say now I will just have the low index material, right, that is going for instead of 80 nanometers, I do it for 240 nanometers and then I can go back to my other routine of alternating layers. Then what do I have? I essentially, if we are able to do this, this corresponds to one mirror on this side and beyond this NL layer, I have another mirror, okay, and these are separated by a thickness of 3 times DL, okay. So, I can make in the same structure, I can make a Fabry-Perot echelon by just by doing this, right. So, let us go ahead and try to see how this structure can give this band pass filter characteristic, okay. Shall we do that? So, to analyze this structure, what do we have to rely on? We go back to this sort of an analysis we did previously where we have multiple beam interference, okay. So, you have multiple beam interference and so in this case it's coming from different layers, right, different interfaces, okay. So, let us just extend this multiple beam interference to the case of a Fabry-Perot structure. So, overall what we have set to do is a Fabry-Perot echelon or Fabry-Perot cavity using this thin film interference concept, okay. So, so what we have said is we have assumed that we are going to be able to make one mirror here and another mirror here, and light that is getting into the cavity, it is coming here, it is going through reflection, it is coming back, reflection, and that is coming here, and then that is undergoing one more reflection and coming back and so on, right. So, if I were to represent the total intensity that is coming out of this, I you say is corresponding to the magnitude of the wave square, and that will correspond to multiple components that are coming together. And what does each of those components represent? So you can actually write this as some component u naught, something you take out as common, and then magnitude of that, and then you have 1 plus h square and so on. That is an infinite series, right. So what is h over here? H will correspond to, if each one of those have a reflectivity r, right. As far as the wave amplitude is concerned, the reflection coefficient corresponds to root of r. So it is undergoing root of r reflection over here multiplied by root of r reflection over here. So overall it undergoes r as the total reflection, and then what is the total phase? E power j phi, where phi will correspond to 2 pi over lambda. Let us say this is a refractive index n, and let us say this is corresponding to a distance L. So n multiplied by 2L would be the round trip phase, okay. So in this case what we will find is this is an infinite series. So the total u is going to be given by root of I naught divided by 1 minus h, okay, and where h is given by r into e power j phi. So the total I is going to be magnitude of that, the whole square, and that is going to be given by I naught divided by, it is the same thing that we did over here that we are going to follow, right. What we did over here is we just expanded it out and had this e power j phi by 2 and minus, we took a e power j phi by 2 outside and we got to this form, and then we were able to convert that to a sine square form. So we are going to do the same trick over here, and when we do that what we find is it is going to yield an expression I naught divided by 1 minus r the whole square plus 4r sine square of phi by 2, okay. So that is going to be the this expression for I, and if you divide the numerator and multiplier by and denominator by 1 minus r square factor, you can write this as I max divided by 1 plus a quantity that we will call as, you can write it in terms of a quantity that we call as finesse. So 2f over pi the whole square sine square phi by 2, where I max corresponds to I naught over 1 minus r the whole square, and that quantity that we are going to call as finesse is going to be given by pi root r divided by 1 minus r, okay. So key thing is, with respect to phi we have a sine square function which is similar to what we had before. So if we were to plot this function, so where we have basically I, so what we will find is you will have these multiple peaks that are going to show up over here, and this is actually as a function of phi. So, what is the between two peaks, how much phi do we have to go? What is the phase difference between two consecutive peaks? 2 pi, right? It's the same thing that we saw over here, right? So that is going to correspond to 2 pi, and what is important here in this case, you know, since the intense, so what we are saying is only wavelengths at only specific wavelengths or specific frequencies are going to be passing through this cavity, right. So, if you want to make this as a band pass type of filter, what you are looking at is trying to see if one of those peaks can be used to show that band pass characteristic, okay. And to do that, one of the key aspects is what is this you know, FWHM width that you have, okay. That FWHM width is actually something that you can find out by looking at the finesse. It's similar to the in electronic circuits, the Q of the cavity. So, that finesse is going to be given by delta nu, where delta nu corresponds to the frequency difference between two successive peaks divided by this small delta nu, okay. So larger is your finesse. To get large finesse, what do you have to do? If you look at that expression for finesse, to get large finesse, the reflectivity has to be very high. To get large finesse, essentially what you are saying is you need to have more number of interfering beams, and you will have more number of interfering beams if you make your cavity with mirrors of high reflectivity. So, suppose you want to design a finesse of 1000, okay. If you plug that in over here, what you will find is to get a finesse of 1000, you will find that your reflectivity would have to be 99.9%, okay, to achieve that, because it's primarily determined by that 1 minus r factor. So, you can almost write it as pi over 1 minus r for very high values of reflectivity, and if you say if f equal to 1000, then r would have to be something the order of, you know, something around 99.9% to achieve that. So, how do we make this structure now? To get that mirror, what do? We have that high and low refractive index material, we make those dielectric stacks, okay. If you have enough number of stacks, you can achieve this 99.9% reflectivity, and then we have that gap that we talked about with the low index region, and then another stack, and so with that we have essentially made a Fabry-Perot echelon. Okay. So there are some interesting things over here which I'd like to go into a little more detail. So what does this delta nu mean? So what is the expression for delta nu? To look at that, let's look at, in this case, delta phi. Okay. So what is the phase difference between two successive peaks, and that's going to be given by 2 pi over lambda 1 refractive index of n multiplied by 2L, okay, minus 2 pi over lambda 2 n multiplied by 2L. See, in this case, what I want to emphasize is that with the Fabry-Perot echelon, let us say the length of the echelon is, length of the cavity is fixed, then you can actually see what is the spectral response provided by that Fabry-Perot cavity. So you know that it is going to have constructive interference for one wavelength, not so good interference for some of the other neighboring wavelengths, and then it is going to be constructive interference for another wavelength. So it is going to be like a periodic series of peaks. And so now what you are trying to find out is when is the next, what is the wavelength corresponding to the next constructive interference, where is that going to happen, right? And specifically we are trying to look at what is the frequency corresponding to that. So we can write this as 2 pi over c lambda 1, you can write it as c nu 1, okay, c over nu 1, that is in free space frequency. So n into 2L minus 2 pi over c over nu 2 n into 2L, and that has to be equal to 2 pi for constructive interference for successive peaks. So this 2 pi we can cancel across over here, and that will give you the expression that delta nu, which is the separation of frequencies, is going to be given by c over 2 times n times L. Okay. So in a Fabry-Perot cavity, this is a generic sort of solution that we get, and we are going to revisit this later on when we go to the topic of lasers also, but essentially what we are saying is a Fabry-Perot cavity allows only certain light frequencies to pass through it, okay, but it is going to allow frequencies that are spaced periodically, and between two successive frequencies which have the highest transmission, you find that that spacing is going to be corresponding to c over 2nl. Okay. So by n is in this case a given, n we have picked as nl. Okay, so that is a fixed quantity. By changing L, you can actually figure out if it is a very small L, then delta nu is very large. That is probably what you want for a band pass filter. You want to pass a particular frequency, but all the other neighboring frequencies or broad range of neighboring frequencies you do not want to pass. Okay. That means that next peak should happen at a much higher frequency, that you can ensure by picking a very small cavity. Okay. So those are the conditions, considerations that you go with, and then of course you are also worried about delta nu. So, if you want to get a very small delta nu, the key thing that you work with is, try to achieve a high finesse. High finesse will correspond to a very small full width half maxima of the peak. Okay, so you can pass one particular wavelength and reject all the neighboring wavelengths. I think in one of the tutorial problems you are asked to crunch some numbers related to this, so you can go ahead and try to do that, but this is essentially the principle of this Fabry-Perot echelon. So, what we have done, we have just a quick recap. What we have done is we have used the concept of interference in multiple layers, as in the case of thin films. We have shown one example where you can get destructive interference, and that is important from perspective of anti-reflection coatings, but you can turn it around to multiple layers and have constructive interference criteria which can be useful for mirrors. Okay. And then we have extended the concept to stack two mirrors and form a cavity, and if you form that cavity, then you can pass only a selected frequency or selected range of frequencies. Okay, you can choose them from other frequencies, or certain colors you want to transmit and all the other colors you want to reject, then this would be the case. So, this is actually very interesting because one of the research projects that we do is establishing free space optical communication, right? It's supposed to work in broad sunlight. Okay, and for this particular link, we are using a green light source, a green laser. So, we are shooting a green laser from here to several kilometers away, and we have to capture that information. Okay, but guess what? What is the biggest problem in this link? Is the receiver, which is looking for green light, is also seeing all sorts of solar radiation during the day. Okay, how do I make sure that it's solar blind, right, and can only allow this green light to go through? Okay, I use a filter like this. I basically say, okay, I'm going to make a Fabry-Perot echelon which is allowing me only to transmit one particular frequency, one particular color, and it's rejecting all the other neighboring colors. Okay, so all the solar background radiation is rejected, and I get a good transmission at the color that I want. So, let's look at another example of corresponding to a multi-slit interference. So, example 2 is once again one of the problems that is given to you in the tutorial. You are asked to design a diffractive element for first order interference. So, this is also a problem that is inspired by something that we do in the lab. There are these devices called fiber Bragg gratings. Okay. What it is just a periodic change in the refractive index of an optical fiber. If I make a periodic change in the refractive index of an optical fiber, what we saw in multiple layer interference holds good. So, I can make a mirror at a particular wavelength, right. So, that is what a fiber Bragg grating is. So, it just consists of an optical fiber in which I have modified the refractive index in a periodic manner. So, reflection from all of these interfaces, they will constructively interfere at one particular wavelength, and that wavelength is called the Bragg wavelength, which will be corresponding to 2 times n times capital lambda, okay, where capital lambda is the period of this high and low refractive index region. Okay. So, I am trying to make this structure, and I am told that I can modify the refractive index of this material if I expose this to ultraviolet radiation. Okay. If ultraviolet radiation falls on this fiber, it will change the refractive index. Now, the question is, how do I create this periodic high and low intensity ultraviolet radiation, right? So, I want to have high and low intensity ultraviolet radiation, so that the high intensity regions there is a change in the refractive index, low intensity regions there is no change in the refractive index, and so on. So, then I can make this structure. So, how can I do that? Turns out that I can do that by using a element that looks like this. Okay. What this element should do is, if I come in with this ultraviolet radiation, it's a large beam that comes in, then part of the beam should go in one direction and part of the beam should go in the other direction, okay, so that there is overlapping of these two beams. So, one beam is going this direction, another beam is going this direction. If I am able to split into two beams, then in the near field, what do I have? I have interference between these two beams, and corresponding to that interference, I have periodic and I have a high and low intensity structure. So, what I would do is I would put my fiber Bragg rating over here, and because you have this periodic intensity changes, then I can make my fiber Bragg rating, okay. And this is what we do in our laboratory, okay. The biggest culprit as far as getting good gratings is concerned, the biggest enemy, can you guess what that is? Is this radiation that is going straight through. The radiation that is going straight through would correspond to the zero order beam. So, let me just go back and show you this thing over here. So, there is actually a wave that is coming in here, setting out secondary wavelets, and they are all interfering constructively at the axial point over here, right. So, if I have the same situation over here, that entire beam will be such a uniform beam that it will wash out all these fringes. That will be like a DC shift in the refractive index change that I get. Any of this beam that is going through, which we call as the zero order interference, will be a uniform exposure of this fiber, which will wash out all these fringes. So, in my case, I do not want this zero order thing to go through, right. I want to find a way to nullify this and only have this +1 and -1 order go across, and they interfere and they give me this pattern, okay. Now, I will challenge you to come up with a solution. right. So, what would be the solution for something like this? What would be the design of this element such that I can essentially cancel out any beam that is going straight down, but make these beams go through the first order interference. So, to cancel something, what do you need to happen? Destructive interference. So, there should be a phase shift of pi. Pi between what and what? There should be two components that you have here. So, which are the two components? Well, those are actually the diffracted components, right. So, those corresponds to constructive interference, but constructive interference between what and what? What are we considering here? This is actually a transparent element. Do you see two different features which can give you two different wavelets? So, I can clearly get a wavelet from these regions, right, but I can also get a wavelet from this other region, this ridge over here, okay. So, I can have constructive or destructive interference based on the relative path lengths between the two regions, right. So, what is my destructive interference criteria? This ridge should be of such height, okay, that these two beams are pi phase shifted with respect to each other, correct. So, if I write that criteria for this to happen, delta phi would have to be 2 pi over lambda, okay. In one case, it is going through the glass of refractive index, let us say n. So, I would say n times h. In the other case, what is the phase that is accumulated? 2 pi over lambda multiplied by in the ridge case, that is also going through the height, but in what medium? In air, okay, which has a refractive index of 1. So, I would say that is actually accumulating a phase shift corresponding to 2 pi over lambda multiplied by h, okay. So, that corresponds to 2 pi over lambda multiplied by h multiplied by n minus 1, and that should be equal to, what do we want? Pi phase shift. We want destructive interference. So, that is pi phase shift. So, I would cancel this, and then that would give me the ridge height should be lambda over 2 times n minus 1, right. If my ridge height is lambda over 2 times n minus 1, then I can achieve this. I can achieve a null for the 0 order interference, because if it's satisfying that condition at one point, it is satisfying the condition across the entire diffractive element, okay. So, the beam that is going straight through, the components that are coming from these crest regions are cancelled by the component that is coming from the ridge region. So, I do not have any light going straight through, right. And of course, you can put some numbers to this, n if you say roughly is 1.5 and lambda lambda is typically, I said UV radiation, right. So, in this case lambda would be about 250 nanometers, okay. So, if n equals to 1.5 let us say, then h is going to be equal to what? The same number, 250 nanometers, okay. So, if you make this ridge height as 250 nanometers, then you can essentially make sure that the central part is cancelled, and then you have interference between these other two regions, okay. So, then the question is, what will be this angle theta with respect to the straight? There is an angle theta at which constructive interference happens. So, how do you find that value theta? So, let us say this corresponds to capital lambda, the period of this diffractive element corresponds to capital lambda. So, in terms of capital lambda, can we find this value of theta? So, for first order interference, delta phi equals to 2 pi over lambda multiplied by path length difference is going to be given by 2 pi, right. That is the constructive interference criteria for the first order, right. But in this case, I am already starting with a pi phase shift between the two components. At this plane itself, they are pi phase shifted. So, my constructive interference criteria, you have to take care of that. So, or rather I can write it in a slightly different manner. So, let me just do this. Plus pi, right, that phase shift you already encountered right at the diffractive element, that is equal to 2 pi, right. In other words, you can take the pi to the other side and do that manipulation. What we will find is this PLD, this PLD will correspond to, like we have done before, will correspond to capital lambda over 2 multiplied by sin theta, okay. So, if you do all this substitution, what you will find is sin theta will be equal to lambda over capital lambda is what you get, and theta will be sin inverse of small lambda over capital lambda. Small lambda in our case is 250 nanometers, and capital lambda, let us say we are given, if capital lambda is let us say 1 micron, okay, then theta is going to be, if you substitute all of this, you are going to be about 14 degrees is what you are going to get. Okay, so that is the other part. One last note and then I will stop at this. The in the tutorial, the other thing that is asked is so this is actually the A part of that problem, this is the B part of the problem. In the C part, you are given that the this incoming beam has got a spatial coherence, that UV laser beam has got a spatial coherence of 1 millimeter, and we are asked to find out what is the depth over which this interference happens. What is that longitudinal depth over which that interference happens. Why is that important? Because I need to know, in my FBG fabrication case, I need to know how close I need to keep my fiber so that I can get this periodic structure. Okay. So I need to know what is the value of D. So how can we find out? Well, if it's a spatial coherence of 1 millimeter, what does that mean? You know that only a part of a section of the beam which is within 1 millimeter, they are going to have interference, right. That is what we saw when we were looking at spatial coherence somewhere over here. We say spatial coherence means that only if the spacing between the two slits, in this case, if that is within 1 millimeter, I can get I can get interference. If it is greater than that, then the coherence actually falls off rapidly, right. So essentially what we are saying is, within this you have a 1 millimeter section of the beam over which that's going to support this interference. So corresponding to that 1 millimeter, maybe I'll use a different color here, go for orange. Corresponding to that 1 millimeter, you are going to have this interference happening. So this depth over here is where you are going to get interference fringes, right. Only over that 1 millimeter region, the beams are going to, although they are crossing each other all across that entire element, okay, only the beam corresponding to a width of 1 millimeter is going to have that memory that it came from the same source, okay. So only that will be correlated, only that will actually give constructive interference. So you can actually say, okay, there is 1 millimeter section, neighboring sections, each of which is interfering and giving you that interference pattern. So that interference pattern can, in the lateral side, can be across that entire beam size, okay. But in terms of the depth that you get, that depth will be determined by these two beams, two rays that are crossing across within that 1 millimeter, okay. So if we do that, so what we will find is that if we say this is theta 1, we can actually draw this again. So we have one beam going this way and another beam going this way, right, and this is at an angle theta 1, which is what we have determined over here, or we can just call it theta, right. So this angle is theta, so you can say this angle is also theta, and if we want to find out D over here, you can write it as tan of pi by 2 minus theta, right, is going to be given by this d over base of this. So, the base of this is actually, what is it? That corresponds to rho c, right, but we are only taking half the triangle over here. So, that will correspond to d over rho c over 2, okay, or in other words tan pi by 2 minus theta is nothing but cot theta equals to 2d over rho c, or in other words what we want to find out is d is going to be rho c over 2 cot theta, and theta we have already found out is 14 degrees. So, if you substitute that, rho c is 1 millimeter. So, what we will find is this is corresponding to 1.95 millimeter. So, you find that the depth of that interference region is 1.95 millimeter. So, I have to place my fiber within that region, preferably closer to the face mask, but certainly within that 1.95 millimeter region to have good contrast interference fringes. If I move it away from that, the contrast in my interference fringes will fade, because the interfering beams are not spatially coherent. That means they are not going to give you this nice constructive and destructive interference. Okay. So, let me stop at this point, and what we want to do now is we have learned some things about wave optics, we learned something about coherence of light, and in coherence of light what it essentially has done is introduced us to the statistical property of light, and based on this we will go back and see where this statistics comes from you know, you will see that it is actually coming from the emission characteristics of light, and that actually brings about the particle nature of light. So far we have been looking at only the wave nature of light, but we will go on to looking at the particle nature of light in the next session. Okay. So, thank you.